Segment 50, Galaxy Evolution. We've talked about the Hubble constant and our ability to map out the universe using Hubble's law as a means of getting the distance. And as we've talked about stars and planets and things like that, we've tended to ignore the light travel time for light getting to us from these distances. But in the case of galaxies at very large distances, the light travel times can approach the age of the universe. So when you look out to large distances, you really are looking back in time in a meaningful way at objects as they were in a much younger age in the course of the universe. The galaxies we have today divide into basically three groups: the elliptical galaxies that are made up completely of old stars and have an elliptical shape with orbits that have a large radial component. The spiral galaxies that are made up of both old and young stars and have a very characteristic disk that's in circular orbit containing most of the young objects and the gas and dust in the galaxy, and then irregular galaxies as well, usually quite smaller objects. But how did these objects form? How did we get to this state? The universe, remember, was made up of just gas initially, and this gas clumped together and started out by, we think, forming smaller clumps that then grew into the much larger clumps that became the galaxies we see today. In the nearby universe, there is evidence for the interaction of galaxies. There are a number of objects you can see that clearly result from collisions between different galaxies. Here are just a few examples of these, and kinematic models of these objects demonstrate very clearly that they can be formed in the collisions of two different galaxies as they interact with each other, as the tides from one strip material off of the other one. Rich clusters of galaxies contain more than 1,000 galaxies. They're very crowded together. They have a large number of ellipticals and few spirals. Poor galaxy clusters, ones with less than 1,000 galaxies, are less crowded and contain a higher number of spirals. This gives you the hint that interaction may be affecting the type of galaxies that are present in these regions. Our own galaxy is part of a small cluster called the Local Group, which has about 50 galaxies, including the Milky Way and Andromeda, and then a number of smaller galaxies. And this group is about a megaparsec across. When you look out to very distant regions, when you look out and effectively back in time, what you find is that a higher and higher percentage of the bright galaxies you see are undergoing collisions of some kind, interactions of some kind. And it seems that the whole evolution of galaxies is governed by interactions and collisions between these galaxies at an earlier time. It's because galaxies are fairly large compared to the distance between them, this probability of these kind of interactions is not low. And when they happen, the results can be very dramatic. Here's a case of two galaxies that have come together, and the image you see on the right is a detail of the image on the left. And this collision has caused the gas to be shocked in this galaxy and started a huge amount of star formation in the inner regions of this galaxy. And a whole burst of new stars are forming, and gas is being used up in this process, and other gas is being ejected. It's a very dramatic event in the lifetime of the galaxy. Here's a picture of the Hubble Ultra Deep Field, and what you see is that as you look to large distances, most of what you're seeing here is galaxies. There are very few stars in this picture. It's almost all galaxies. And some of these galaxies are very much like the ones in our local universe, but some of the smaller ones, which are the more distant ones, are part of these interacting systems. And we believe that galaxies build themselves up from smaller units over time, colliding, merging together, forming new stars, and gradually become the galaxies that we see today. So here's some pictures, a blow-up of that last picture showing some of these amazing objects in the ultra-deep field. The foreground ones are these larger ones here, and then you can see the smaller ones that have all sorts of different shapes and sizes, and actually different colors as the degree of star formation going on in them at the present time is different. The object you see in the middle with a cross is a star in our own galaxy that shows then diffraction spikes from the telescope because it's a point source. So what we think is happening is that starting from the Big Bang, which we'll talk about in the next lecture, the universe is all made up of this smooth gas that is embedded within a matrix of dark matter. There are small fluctuations in the density in this dark matter, and those fluctuations grow with time, and material falls into them, forms seed galaxies, which then merge together with more infalling material and interact with other galaxies to form the galaxies that we see together. The amazing thing is that when you look back in the universe to when it was only a little over 1 billion years old, you're already seeing big galaxies very much like the galaxies we have now, although in addition to that, there are many of these smaller objects as well. The study of the evolution of galaxies is a subject that's still unfolding now, and we're hoping with the James Webb Space Telescope, which will be the successor to the Hubble Space Telescope, to be able to push back into the so-called dark ages when the first stars and galaxies formed and trace this evolution all the way through to the present to really understand how it takes place over time.